This video is the for Thursday, and our date on Thursday is the 13th, and we're just checking the homework from last night, which I'd like you to do also, and then maybe as I do explanations of people's questions, you'll be able to get the answers there as well as to why these work. Okay, a lot of people had trouble with both 18 and 19, am I right?
Yeah.
Probably more than half the class had trouble with both of those. Your question, Gavin, was on 19, so I'll address that one first. But as you look here, you're going to see, all right, so down here on 19, that was fun. Little chart move. Here we go. You'll see we have a relationship here. This is called the mole-to-mole relationship. Okay? And the balanced equation. That was critical to both of these. Okay, this guy needed a balanced equation as well. In this problem, we were comparing reactant to reactant. Here, we were comparing reactant to a product being formed. Okay, so they presented this problem as a manufacturing problem. We're going to make this stuff, okay, and we're going to find out what the the calculated amount is that we can get on this. And what you're seeing right here should be very familiar. But they called it something different, didn't they? Yeah. They called this the concept map. Okay. What I have been calling the big picture is a concept map. It's one kind of concept map. There's other ways to do this. But I thought in my answer that I gave to you guys, because it in my mind made so much sense, is to take it like here, and so this stuff going across here is what I'm referring to as the concept map, and the chart is one way that we get from given of the grams to moles of the given, which is hydrochloric acid. And then the mole ratio here is going to take us from moles of one substance, the hydrochloric acid, to the other substance, which was calcium chloride. And then with the chart, we can get back into using the molar mass, the calcium chloride grams. That's all. Yeah. It sounded a whole lot worse than it was.
Yeah.
A whole lot worse than it was. Okay, I'm also getting a question on number 18, so we'll go back and look at that again. Here we have our concept map, and here is the balanced equation. Essentially exactly the same thing, just different substances. However, on this one, we worked with reactant ratios. With this guy, we're working with reactant and product. So that's the only difference between these. Here, the question was, I'm going to make two things come together to form one thing. What do we call that? What do we call it when we're putting two things to become one? Synthesis. Okay, so this guy was a synthesis reaction. Now this guy, we've got some other things going on, but basically what do we have here? It's like a double replacement. The only difference is that we're producing this gas, and that gas takes some of the stuff out. So it's sort of like a double replacement. The only thing here is that we're producing a pure liquid, and you know, that's all irrelevant in terms of this particular question, but I thought it was interesting to just look at. So right here, same old, same old. Okay, you're using the concept map, and that concept map is going to take you over to a product from a reactant. Or in this case, taking you from the given grams of one of the reactants and making that into moles, and using the mole ratio from up here to get over to here, and then using the chart to get back to the next. Does that make sense? Okay, good. Because sometimes you have to hear it more than once. See, I talked about that before, but somehow when you're asking the question, it's a little more meaningful. Okay? Okay, so you're good now. Yeah, all right. Okay, we got the question on 19 again, so I think what we'll try this time is looking at the actual question and then relating it back to what I did down below. So let's go on up here. Many cities use calcium chloride. Do you know which one that is? Okay, good. That's this guy. To prevent ice from forming on roadways. And we'll be talking about that in a future chapter. To produce calcium chloride. Ah, okay. This was nice stuff to know. It had nothing to do with the problem. Are we good then? Okay. To produce calcium chloride, aha, we're going to have a balanced equation. So there's our balanced equation.
So it's already given to you?
Oh yeah, it was given to you. Okay, so is reacted with hydrochloric acid according to the equation. So all of this is useless because all we really needed was this guy. Question's getting simpler, isn't it? Yeah? Okay. That's what I figured we needed to do. Create a concept map, and you understand now from my prior reaction, or my prior responses, thinking reaction, from my prior responses that this big picture thing is simply a concept. So when it says up here to create a concept map that describes how you can determine the mass of calcium chloride produced if the mass of hydrochloric acid is given. That is why this, now, yeah, that connected, did it? Good, great, okay. Did that connect for anyone else? Yeah? Okay, good. Good, I'm glad we went there. Want to delete? This is what I'd like you to do now. Copy the percent yield and then turn off the recording. Or, I'm sorry, stop the recording as you copy the concept map. So here, theoretical, although it looks like a big deal, it's calculated using a balanced equation. Does this sound familiar? Stoichiometry. That's what you were doing last night. Okay? So, or night before last. And so this theoretical thing is no big deal because you've already done it. But the actual thing is even less of a big deal because they have to give it to you. Not bad, huh?
Also, it's forgiven.
Now, the only thing that you have to worry about in this whole thing is that whatever unit of measure the actual is, theoretical must be in the same unit of measure. Or vice versa. Theoretical can wind up stopping at moles. It doesn't have to go all the way to grams. Or you could take it to grams if you're given was grams, but I like stopping at moles. Yes?
The yield that's taking between a product and a reactant.
Yeah, the yield is one of those deals where, oh, I did a great deal in one of my periods, and I get to repeat it here because I remembered it on the recording. How many are Armenian? Okay. Any one of you, I'd like you to volunteer, if you will, to tell me how much food is cooked for an Armenian meal compared to how much is consumed when the people sit down to eat it. I can do it. It's universal, isn't it? Anyone? What? You eat about a third? Whoa, 30% yield. Oh, anyone else? Yeah, what do you have in your house? 20%. Whoa.
89.
You mean you put
All of it.
you have to store 80% of what's cooked? Wow. Okay, if you store 80% of what's cooked, your percent yield is 20%.
Yeah.
In other words, they're eating 20% of the meal. Or 33%, Or what else did we have?
257.
Yeah, 257%. Yeah. Okay, so percent yield is very simple. There's two kinds of yield. If I take a gun and I put it to your head and I tell you yield or I'm going to pull the trigger, what do you think you would do? I think you'd yield. Okay, when you drive into an intersection and you're going to make a left turn, who has the right of way? The oncoming traffic. Okay, oncoming traffic. So, what do? You yield to the guys that are in the oncoming traffic. You don't make your left turn in front of them unless you're fond of being hit. Yeah, well, even if it's a signal. Yeah, if the signal gives you the green light, then you don't have to yield. Okay, the yield we're talking about here is like the Armenian dinners. Okay, 20% or whatever. Okay, in most chemical reactions, you'll get 50% or better. But very few chemical reactions will have 100% yield. It just isn't going to happen very often. Okay? When you have a problem like this, does this look like calculation time?
Yes.
Oh, yeah. So, what do you have to copy?
Even everything.
Equation for sure. What else?
The amount of
Given and time, sure. So, did any of you do this?
Yes. No, because I didn't copy.
Right now, before we go any further, I'd like you to copy down the given and the find. And turn off your recording while you do this. Now, as you look at this problem, you may not understand the difference between this guy and this guy. Is there anyone who would like to tell me? What's the difference between these two guys right here? 684 is the what?
It's like the total amount you have, and then the 349 is the one that you use, right? Or
No, I think you have it backwards.
oh,
Okay, the 684 grams of glucose is used to form the alcohol. Okay? Maybe that wasn't very clearly written. But this guy is your given. He is the amount that you are starting with, and that is right here. Okay? This guy is what you're going to end up with as an actual, which is this guy. The actual is we do the reaction and we see how much we get at the end. And after the reaction stops, we're going to measure how much alcohol did we produce. That you cannot calculate. That is given to you. So without doing the experiment, you have no way of knowing this number right here. Okay, let's go and look now at what's up next. This should look very, very familiar. This is called the theo. That's right, theoretical. I call it theo for short. So, we start out here. So, this is the given. That's the stuff that we're starting with. And if we look back at the balanced equation, you'll see it there on the left-hand side as a reactant. Yeah? So, how are we going to get this number? Where does that come from? This should help. If you don't understand yet, you will in a second. Yeah, from the chart. Right. So we add it all up and we get that number. See, here's all the numbers that we put together to come up with the molar mass. Now down here, we're actually putting the 342 grams on the bottom, and that's the grams that equals 1 mole. Okay, that's why we can make that fraction. So let's go. There we go, just pack it back up. And now, where did this guy come from? This fraction. Balanced equation. Okay. 4 is the coefficient of the alcohol, right there. And 1 is the coefficient of the sucrose. Okay? So, that's theoretical. That part, that's nothing new at all. Okay? That's just same old, same old. Now, to get the percent yield, that's a little different issue. Okay, so percent yield, we first get the actual amount made into the same units as the given. Well, the given wound up giving us this stuff, and we wound up with moles. Same units as the calculated Theo amount. The actual amount made into the no, I had that right. No, this was correct. Nope, no, that's correct. Same units as the given. Oh, okay, what's the given? The given in this case, the actual amount, this is your actual amount right here. Right down here. Now, I stopped at moles. I could have gone to grams, but I opted to stop at moles. So since this guy was given in grams, I'm going to put him into moles, and then everything will work. And so when I run these numbers, and you all understand, I think, where I got this. Yeah? Okay, good. So let's put that back away. And that's where we're going to get this number from. Now we're ready to do the percent yield. Look at your notes on percent yield right now. And let's go back down here and check and see where that all came from. You got it? The 8 from what was theoretical, that's how much could be produced if the reaction completed. 100%. Okay? This obviously did not create, or did not complete 100%. It's very close, but it's not 100%. Why do we have the 100? Because that makes it a percentage. Yeah. Okay. So that's it for all the guys that we're going to be doing that have anything to do with percent yield. It's just getting the actual that was produced. That's where this came from, and put it over what we calculate is possible. And these numbers will hardly ever match. So, by the way, could we have more produced than we calculated?
Yeah.
How would you do that? Where's it going to come from? You've used it all, folks. If you used it all, there ain't no more. Pardon my bad English, but it's all gone. And I think this next slide is kind of interesting. Let's take this. And let's take this a piece at a time. I think a lot of people misunderstand this. If I get 100 pounds of reactants, 100 pounds, all right? If I weigh my reactants and my products before I react anything, what is the mass of reactants going to be? Okay, no reaction has gone on yet. We have not mixed the chemicals. And so, how many pounds do we have of reactants? Daniel? I haven't reacted a thing.
100 pounds.
Very good. And how much product would you have? Huh? Okay, so you're going to make 100 pounds into 200 pounds without doing anything. That's what you're talking about. What you just said means you're going to take 100 pounds of reactants and turn it into 100 pounds of reactants and 100 pounds of products at the same time. Okay, if you haven't mixed them, how can you have a product?
No product.
No product, yes! Now, Daniel, don't feel bad. I had someone who has 105% in this class that did exactly what you did. Okay, so before anything happens, 100 pounds, 100 pounds. Now, if I have 100% yield and I mix my reactants together, Arthur, what am I going to have in reactants? I get 100% reaction. So I'm going to have 100 pounds of reactants after I react everything together. And how many pounds of products would you have? This isn't before anymore. This is after. After. Okay, you're going to mix oxygen and hydrogen, right? You light the match. Before you light the match, you have, say, 10 grams, reactants and products. I'm sorry, of the reactants. You have 10 grams of the reactants. Okay, you light the match. You get 100% reaction on this one. How many grams of reactants are you going to have after you light the match? 0. Okay, good, you got it. All right, then you understand. I just wasn't saying it right for you to hear. So, in this case, we have a 90% reaction. You see why it's 90%? Because we only got 90%. Okay, and that means we have to have 10 pounds left. Because 10 pounds of reactants failed to react. This is called a 90%. This is a 90% yield. Now this guy is 100% yield. So before, yeah, it's a synthesis. Before I react, I have 100 and 0. What do I have after I react, Raphael? Absent. Yeah, okay. So what do I have after they react? They go 100%. Yeah, this is going to be 100% yield. What do I have for reactants when I'm done? Huh?
0.
Good. And what do I have for products? Yes, because this represents 100% yield. Okay? Does that help? That's. I found after I did this that people were getting it a lot better. Okay, so that's how we did this guy. And what we're going to do now is give you an opportunity to work this problem. So turn off the recording, work the problem, and then check it out. Now we're looking at the given and find, and you can see just like the last problem that the Theo is the lead oxide. That's what we're going to calculate. The percent yield then will be the percent of lead oxide that we make compared to the Theo. Theo is 100%. Okay? If we get 100%, it'll equal Theo. But most times that doesn't happen. So, has anybody started the problem? Okay, go ahead and start, and I'll stop the recording. Okay, so we're good on the first fraction. So Theo is just like you would think it is. Okay, we started out with the 200, which is the starting amount of the lead sulfide. Then we're going over here, and we're making the lead sulfide. You know what we had to do to get this number, don't you? Where did that number come from? Okay, good. Molar mass from the chart, and that's the amount of grams that equals 1 mole. And where did the 2 and 2 come from? Okay, yeah, we got PBO and PBS. So here's the PBS, here's the PBS, and here's the PBO. And so when we draw our lines to connect those guys, or the arrows, this is what we're talking about here. That's the ratio. Now, how do we know who goes on the bottom? Okay, on the bottom has to be PBS, and the reason that has to be PBS, let's move this down here. PBS has to be here, lead 2 sulfide, because we got PBS up here. And the moles of PBO come from that little arrow that I just wrote up there. And we wind up with the number 0.836 moles of lead oxide, lead 2 oxide. Then actual, just like in the last problem, we're taking the actual, converting it to moles, and we get 0.762. So let's see if somebody can figure out how we do the next step. Edgar, what's going to be next? Oh, yeah, he's gone. David Saturian. What's going to be the next step after this? How are we going to use these two numbers? Okay, we're going to make a fraction. And what's going to be on top? Good. The actual that we just calculated, this stuff. And let's put the actual in a red color just to kind of keep it separated. Okay, let's make all this red. And there we go. We've got this in red. So the red's going to go on top. Is that it? Yes. The red goes on top. The blue goes on the bottom. That's the PO. And that's what we have here. So the percent yield has got to have 100 in it to get it to percentage. And our answer should be 91.1. We'll be doing this after we come back, and you've got two nice examples in your notes here, so you can refer back to them as we're doing our thing. I hope this helps a lot of people. So long for now.